risen. Hallelujah, hallelujah. Truly is risen. Hallelujah, hallelujah. All right, guys. So, first off, once again, my apologies to Benjamin, to Leo, to Natalie. Yes, you were in my grade 9 science class before. So, I apologize if I forgot your names. Okay, all right. So, that being said, any questions? The homework.
Yes, I have one. Let me find it.
Yeah, you raise your hand, guys,
Oh,
first.
okay.
Okay. All right. So Max's question:
To be,
to be or not to be? Okay.
not to
What?
be.
Okay. What page?
Page 548.
548.
Yes.
548. 548. Number 2B or not to be. Okay. Okay. Anything else, guys? You have another one like Max?
No, that's it.
No. Any more? Yeah, Madav?
Can we do number 17 and 19? I'm just going to check the page.
17 and 19?
Yeah, on page 575.
Yeah, okay. 17 and 19, you said, right? Okay. Okay, any other one? That's it? Okay. You can lower your hand, Madav. Okay. All right, so let's start with this here. Oh, Jason. Wonder if I should admit Jason. Yeah, I guess so. Okay, so just give me a second here. I will share poor little computer. Benjamin, like to? Perhaps he was offended yesterday. All right, so let me sort of put this here, which you don't see. There we go. Okay, so number 2B, not to be. So electroscope with surplus discharges. What do you want? You want to find the current? Okay, so 2B. So you have a surplus. So if you have a surplus here, the charge here will be like that many surplus, right? Electrons times the charge of one electron, right? So it's going to be like 2.2 times 10 to the 10 times like 1.6 times 10 to the minus 19 Coulomb. And then this is going to give you like how much current is being discharged. So it's going to be 2.2 times 1.6. I don't know what it is. It's like 3.2, 3.2. So about this, something like this, I think. If I do it like quick in my head. And then you're looking for the current. Well, you have the time, right? The current is just Q over delta T. And the time is 0.6 seconds. And then you just plug everything in, Max. Are you good?
But when it says like surplus of electrons, right? So that means like n plus minus n minus equals to wait. So
Surplus.
n minus.
N plus minus n minus. I mean, as I said here, this is a technical formula, but usually we always give in terms of how many more electrons there are than protons, or how many less electrons there are from protons. So that's why like the n here is usually like the surplus or just the deficit of electrons. So you have like 2.2 times 10 to the 10 more electrons than you have protons. Okay.
But then wouldn't that be negative then?
Yeah, I know, but I told you like you don't put negative signs. Okay.
Oh, okay.
Yeah, you don't care about negative signs.
Oh, okay. All right.
Because in electricity, we know it's always electrons. And then another also reason is because we're dealing with conventional current, so it should be positive.
Oh, okay. All right. Thank you.
Yeah. Yeah. What is that? Chat. Who's chatting? Can we also do Jason Tate? Well, Jason, you came in late. I wonder if I should. All right. So number 17. So page 576. 576. 576. Number 17. All right. So that's good. Number 17. Microwave. So you know the potential difference. You know how much energy. So 50,000 joule. You know the time. 60 seconds. And what you're looking for this, right? Well, you just use this formula here, and I delta t time delta v, and you've got everything. I'm not so sure why it was difficult, Madav. I don't want to put you on the spot here, but what was hard here, or Madav?
I didn't use that formula. I solved for the charge with W is equal to Q times change in V. And then after that, I used the I is equal to Q over change in
Yeah,
T formula.
you should get the same answer though. So you found the charge, right?
Yeah.
Right. So it'll be like 50,000 joule divided by 120 volts. And what did it give you?
I got 417 coulombs.
417 coulombs. Okay. And then what did you do next?
I figured out the currents with the formula I is equal to Q times change in T.
Yeah, it should give you the same answer.
Yeah, I got like 25,000 amps, but the textbook's answer was like 6.9 amps. So I'm wondering, like, I went very wrong somewhere.
Because this is the same equation here. Like this Q here is exactly the same as this. So I don't know if someone can help me here. I don't know if there's a mistakes in textbook here. Let me see here. So you got like 5,000. So what is this? 417 divided by 60. Where's Forest? Usually Forest is right on top of things. So it gives like 6.95 amps.
I got 6.95. Yeah, 94.
Yeah, it's 6.95 amps, right?
Yeah, I
I
probably
think that's
made a
correct.
mistake in my formula.
Yeah. Okay. Good. All right. Done. All right. That happens to everyone. Yeah, even Benjamin. Okay. So electric motor is used to do this much work. All right. So you got the work, which is nothing else but the energy, 2.3 times 10 to 14 joule. If the motor draws a current, so here of 3.2 amp in 30 seconds, and I guess they ask you for the voltage. Yeah, so perhaps you may have made a mistake. Why is Natalie was okay? So once again, you just use the same formula here. Delta T type delta V, and you just isolate for delta V, Madav. You think you did a mistake again? A calculation mistake?
Yeah, I think I just multiplied instead of divided.
Oh, okay. All right. Good. All right. 21. So 21. How much energy? So how much energy is required to run a leaf blower if it draws a current of 13 amp from an outlet, 117 volts, for 10 minutes. All right, so you've changed into seconds, of course, and then you get 600 seconds. Okay, Jason. Well, you just use this equation. That's it.
It's
just
no, 21 is the question about how much energy is gained by an electron accelerated through potential difference of.
Sorry, I'm doing. Okay, thank you. Apologize. Okay, so How much energy is gained? All right, so this is an electron right here. I remember here, so we pretend, of course, it starts from rest. You remember electron left to itself goes from naturally from low to high. So low potential here, right, to a high potential. So potential. So, and the difference between the two, difference is 2.4 times 10 to the 4 volts. So what you're looking for, you're looking for the energy. Of course, what they're asking here is they're asking like how much kinetic energy has been gained. So here the initial kinetic energy is of course 0 because it starts from rest. All right. Yeah, even if it didn't start from rest, I mean, they just want you to find like how much kinetic energy it has gained. So it doesn't really matter here because what you're looking for delta K. That's what you're looking for. Well, remember here, like electrical potential energy, electrical force is a conservative force. So it means that there's a associated potential energy function associated with this. And what you have here is that you have the mechanical energy of this object, of this electron, is made up of 2 parts, made up of kinetic energy plus the the electrical potential energy. And since it's all conservative here, so there's no loss or gain in mechanical energy. So what you have here, you have this. All right, it's exactly the same thing as for a mass, right? So if you let a mass go down, oh, this is lagging. Let a mass go down, all right? It's the same thing as asking you like, okay, so how much energy, how much kinetic energy the mass has gained as it has fallen through, let's say 2.5 meters. That's the same idea here. All right, so this is equal to what? Is equal to this, okay? And then it's an electron, so the charge of electron is this, right? So minus, and this is the elementary charge electron here. So if I put this right here, enemy of an enemy is a friend, so it gets this. And then you just put like everything in. So minus Coulomb times 2.5 times 10 to the 4 volts. Is that okay, Jason?
Yeah.
Yeah. By the way, here, like this is something for next year here. You can see here that for little particles here, the energy gain is not given in joule. It's given actually in electron volts. So for this one here, for this electron here, I know there's a certain amount of joule here. I don't know what it gives you, but it gives you a certain amount of joule. But this also could be written as this, as so delta V here could be written as this times 2.5 times 10 to 4 volts. And that would give you 2.5 times 10 to the 4 electron. So I'm bringing this like just times volt. So this is called electron volt. And this is a unit of energy too, okay? So very often in particle physics, we give energy in terms of electron volts, not joule. Yes, Madhav?
How do we know to say kinetic energy instead of electric potential energy?
No, they want you to, they want you to sort of ask you like how much is gain energy? Well, the energy that is gained here is kinetic energy, right?
Okay, thank you.
Right? It's losing. I like this. This is one of my favorite, Dirac, Paul Dirac. Very interesting fellow. Okay. I think you multiply instead of divide. Okay, Catherine. Okay, so that's a little bit late. I don't check my chat. Sorry, Catherine. Okay, so any other questions? All right, so let's move on. So once again, those who had me in and grade 9. So let me see here. So let me see how I get this right here. I'm not going to forget Natalie, Benjamin, Leo, Luke, Jason, Timothy. Okay, who am I missing here? That's it? Okay. Oh, Sean. Sorry, Sean. Sean, there we go. Okay. So you're going to see here, like what I'm going to teach is something that I've taught you in grade 9 for the most part. Okay. So it'll be like more or less like refreshing for you. Okay. So let's go back to this here. So make sure that you have that. Okay, so we know that current is the flow of charge. Let me sort of share this again here because it's lagging and driving me nuts. So let me share this. There we go. All right. So we learned about potential difference. So potential difference is to electricity what a change in height is to gravity or difference in pressures to a water pipe system here, right? We learned also about currents, which is the flow of charge. We talked about also the conventional current. So here I have a little battery. Ooh, I made this like bigger. There we go. Here I have a battery. It's connected to a single wire. Of course, I made it like super big here. So don't do this at home because once again, this is called a short circuit. And of course here, what's moving in electricity or the electrons, the tiny electrons, the valence electron, not at all the atoms, okay? We're not dealing with plasma. All right, so it's the valence electron. So the valence electron here will, so if we set a potential difference across the battery, the electron will go from low, the negative side here, right, to the positive side. Now, if there were no like atoms in the way, so those electrons will keep on accelerating, so pick up kinetic energy along the way. Okay. However, it's in a solid. And what happens is that those tiny electrons here, they're symbolized by those tiny dots here. What they do here, so once they leave the atom, of course, the atom is positively charged. So once the electrons break free, it accelerates, but unfortunately here, it bumps into the atoms of the metal. So the bumps, it recoils, picks up speed because in different direction, collide with the other atoms and then or molecules and then recoil and then pick up the speed. So the electrons here has what we call resistance, right? There's our forces like akin to friction, so to speak, right? So they're not allowed to sort of pick up like as much speed as they want because they constantly bump into the atoms of the metal. Now, the atoms of metal, when there's collision, of course, the atoms of metal will jiggle. Well, if it jiggles, you know what happens. So what happens to when in solid, the tiny particles are jiggling more? So what happens? Anyone? Yeah, Madav?
Temperature increases.
Yeah, temperature increases. And this is why in electricity, you have always thermal. I'm sorry, I'm looking at this. I hate like talking to a camera. It doesn't seem like, anyway. So yeah, it it jiggles more. So the temperature, of course, like does increase, right? So that's why there's always thermal energy, except for a specific like type of material. There's always like thermal energy that's going to be created, and this is called resistance. All right. So the electron constantly blah blah. So we talked about this. So collision with the electrons. So it will cause. Let me sort of put this like a little bit to the side here. It will cause the electrons to move at constant speeds. Well, this is like, yeah. So on average, the electrons move at constant speed, right? They pick up speed, they recoil, they pick up speed, They recoil, but they move more or less at a constant speed. And you might be surprised to see how slow it is. You think it's fast, but it's not very fast. It's on the order of about centimeter per second. So it's very, very slow. Yeah, so temperature of the material has gone. So what happens here is that if there were no like core here, if there were no cores, all this, so these electrons here will pick up like kinetic energy at the expense of electrical potential energy, right? The electrical potential energy of the electron will go down, and then as a result here, kinetic energy of the electron will pick up. But because of bumping, continuous bumping into the atoms, what happens is all this kinetic energy here is transferred into thermal energy, right? For the most part. So the resistors. So this is where like the resistance comes from in electricity, okay? All right. So any materials, any electrical devices, including a wire, does offer resistance to the flow of charge. Okay, so this is something you should have learned also in grade 9. It so happens there's a relationship that exists between how much current flows through a device and the voltage across the device. So now I'm going to sort of show you like an analogy here. And yeah, so let me sort of share my screen. All right. Oops. You see my screen here, guys? I don't know. Do I have to double click here? There we go. Okay. So it's not what I want you to see here. That's what. Okay. So I apologize here if I put like, I was looking for analogy. I knew what the analogy was. And the first diagram that popped up was something from Wikipedia, but it's okay. It's valid. Okay. It's quite valid. Okay. So this is what we have here. So what we have here is a pipe, and here there's a bit of water above, and so that will sort of provide here like this body of water here will provide pressure, and I will sort of go through this little pipe right here. Now, if the pipe becomes clogged with hair, the pipe becomes clogged with hair. If you want to have the same amount of water, same amount of flow of water going through this pipe, well, of course, you have to increase, you have to have like more water on top of it. In other words, you have to have a higher pressure than before, okay? For the same flow of water through it, if you increase the resistance, the pressure must be higher, okay? For the same flow of current, for the same flow of water. And it so happens here that this is linearly proportional for the most part. So what it means here, it means that the pressure here is proportional to how much resistance the hair offer for the same current here, for the same current. So the more resistance there is, the more pressure you need. So linearly proportional. For current, that's exactly the same. So some material will offer more resistance to the flow of charge, to current. So if a substance has more resistance and you want to have like the same amount of current going through it, you have to set this device across a higher electrical potential difference. Remember, the electrical potential difference is to electricity what difference in pressure is to water pipe system. Okay. All right. So let's go back to let me share this again. All right. Okay. So what happens here is this, is that for a given, now we're looking at a given resistance, a given resistance here. So let's say here you have a pipe with a certain amount of air, and let's say here that you want to make sure that there's more water going through the pipe. So of course you'll have to increase the pressure, the body of water above, right? Well, this is what happens here. So Ohm's law tells you the following. It tells you that the current is proportional to the voltage, or vice versa, okay? Any device that displays, this is what Ohm's law is, right? This is Ohm's law here. Any device that displays this behavior, this linear proportional behavior, is called an ohmic device, all right? So ohmic device obey Ohm's law. All right. And of course, the constant of proportionality here is, of course, well, if you do this here, if you put a constant proportionality in front, what you're going to have, something like this. So let me put this here. Okay. So you do a constant proportionality here, this is what will happen. Now, G here is called conductance. And conductance is just the reverse of resistance. That's nothing else but the inverse of it. All right. All right. So this is this exact same thing as this here, right? Instead of putting like the I on the right, we're putting the I on, no, sorry. Instead of putting the I on the left, oh, I have a problem with my right and left. You're putting it on the right, okay? So you just change this. So this is Ohm's law. Ohm's law is given in this. So if you plot like the voltage across the current that goes through, of course, you're going to have a linear relationship. And the slope will be, of course, 1 over R, which is the conductance here. Okay, so this is like conductance, okay? But we don't talk too much about conductance. We talk in terms of resistance. Now, why do I put a graph, I versus potential? Why not like potential versus current? Because it's way easier. You remember here, like this is the independent variable. It's a lot easier to change the voltage across a device than to change the current, right, through a device and then measuring the voltage across. Okay, so that's why it's written like this. So it's way easier to change the voltage across a device and then measure the resulting current as your dependent variable. Okay, so that's why it's given like this. All right. Okay, so if you look at Ohm's law here, you can, so resistance is given in ohm, in honor of ohm. And the symbol for ohm is a omega, the capital last letter of the alphabet, omega. And the capital one, the uppercase, all right? So you should be familiar with this. Okay, you good? All right. So now let's go back to okay. Go down. A load is any device that converts one type of energy into, that takes in electrical energy and converts into some other form, all right? So that's the definition of load. Across a load, there's always a drop in electrical potential. There's always a drop across the electrical potential. And the same way here, as this water here flows from high to low height, there's a drop and does work on the paddle wheel. There's a drop in height. As the current goes through the electric motor, it experiences, it's a load, it experiences a drop in electrical potential. Sometimes we call this a voltage drop, although it should be really called an electric potential drop, because a voltage is a difference in electrical potential. So, but anyway, so there's a voltage drop right here, okay? It's a device that limits the current because there's resistance, right? All right, good. So let's talk about this here. Okay, so this is something that you should have learned like in grade 9. It's lagging, it's coming. Wow. There we go. Takes its sweet time. Okay. There's two types of major arrangement electrical devices. One is called in series. So if you recall from grade 9, in series means that the same current goes through. So like right here, so the current that goes through this light bulb is the same as the one that's going to go through this other light bulb. So we say that both those light bulbs are placed in series. You have another arrangement that is called parallel. Now, parallel is defined as this. We're going to parallel is defined as the current splits, not necessarily evenly. It's going to split, so the current comes in, split, goes through each device without going through any other device, and rejoin right after. So whenever you have this, those electrical devices are said to be in parallel. Yeah, they're said to be in parallel here. Another definition of parallel is that the voltage drop across devices are in parallel are always the same. So the voltage drop across the resistor, across the resistor is the same as the voltage drop across the light bulb. Okay, that's another definition here, also of being in parallel. Our ammeter, as we said, is something that measures the current and must always be placed in series. So here, if you want to measure how much current goes through, this is called a branch here, how much it goes through this branch, you put the ammeter here. You can put it here, you can put it there, you can put it there, you can put it here. It doesn't really matter as long as you put it in this branch here, okay? And that measures like the current going through R2. A voltmeter, we talked about this. A voltmeter is the device that measures the voltage across 2 points and must always be placed in parallel. Okay, so here, this is the voltmeter here, and the voltmeter is placed in parallel with the device that you want to measure. So here you want to measure the voltage across the resistor. So you place it like this. By the way, here, this is the red terminal here. This is the black terminal, remember? If you want to get a positive value out of this. The symbol for voltmeter is V or G. That stands for galvanometer. Okay, so you should have learned this. You good? Okay. So grade 9. So let's do it a little bit the property of grade 9 here. So you don't have this here, right? Don't really need this. So grade 9. So what do we have here is we have a 9 ohm light bulb with a 9-volt battery, and then there's 1 ohm of current being drawn by the source. Now, if I put another light bulb in series with the first, what happens here is that I'm increasing the resistance of the overall circuit. If I'm putting the same type of light bulb, so this circuit here experiences twice as much resistance. For the same voltage drop, right? Or for the same pressure, right? If I put twice as much hair on my pipe, I'm going to have like less water going through. I'm going to have like probably like half as much water. Well, this is exactly what happens here. So by increasing the resistance by a factor of 2, the voltage stays the same, then the current will be half as much. And then on the last, because I cannot see this here, like, so the last one here, you're putting like 3 light bulbs. So you increase the resistance by a factor of 3. For the same voltage, you're going to have like a third of how much, a third of the current will be able to be drawn by the source, okay? So the current will go up will go down by a factor of 3 compared to the original, right? Okay, so now for those who had me, like you remember this because I showed you that. So just listen here. All right, so hold on a second. Hold on a little bit here. Close this. Okay, so how do I? Okay, pin video. That's not what I want to know. Oh, anyway, okay. That was just a little. All right, so I have a glass of water here. And if you were in class, I would sort of do this with you, but I don't. So what I do with students, what I do with the grade 9 students too, I ask the student to have like a straw here. I gave them a straw, certain diameter. I ask them like to draw water for 2 seconds. Draw water in to keep, like not to swallow the water, to just take note of how much water has been drawn in 2 seconds and then swallow it. All right. Now, what I ask the student to do is this. I take like 2 straw, same straw, okay? And then what I'm going to do is I'm going to put them, I'm going to connect them, one end, the end of the other one. So let me sort of do this here. It's a little bit hard here. All right, so let's see here. Okay, I haven't done a good job here, so it's not going to work very well, but okay. And now what I do is I ask the student to draw with the same power. I don't like the word power because it's not exactly what I want. Actually, what I should say here is that draw with the same difference in pressure, but he understands usually what it means with drawing with the same power. So draw with the same power for 2 seconds, and then keep track of how much water you have in your mouth, take note of it, and swallow it, all right? And now before I do this, I ask for predictions. So what do you think, like this student here with this straw here, right? What do you think? Do you think he's going to be able to draw as much water as for 1, or less, or more? Okay. Yeah, yeah.
Maybe like half the water.
Yeah, there'll be less, right? There'll be less. Why is there less water being drawn, guys? Madav? We're the same people. Madav?
Is the water has to be drawn up a further height?
Ah, okay. That comes to another misconceptions. Okay. So misconception is this. I understand here it's full of air, so I have to remove the air. But my experiment, if I want to do this like very quick, very good here, what I would have asked them to do is to remove the air, get the water in the straw, okay, and then start 2 seconds, okay? This is something that is a misconception here. So let me go back here to this here. All right, hold on a second. I'll share with you. It's a good point. How much time we have? All right, so let's go back to this. All right. Okay, very often like students think like, let's say there's a switch here and then I turn this on. Now students like say, oh, well, the current here has to travel all this before getting to the motor. So there'll be a delay. Actually, there's very little delay. When you open your faucet in the washroom, sorry guys, when you open the faucet in the washroom, that's only my sister-in-law. Don't worry. All right. So so when you open the faucet in the washroom, you don't have to wait for the water to travel because water is already in your pipe, right? So when you open this, you just allow like a difference in pressure to push like the water. Same thing for this here. In electrical circuit, you are providing electrons. The electrons are in your wires in the electrical devices. So as soon as you close the switch, everything, all the electrons everywhere in the circuit almost instantaneously get into motion. Not quite, because there's, anyway, we'll talk about this perhaps later, but almost instantaneously. So when I come back to this here, there's already water in my in the straws. Okay, so it's not because it takes longer time for the water to go through. Okay, so let's go back to this. So why is there like less water when I have like two straws like this? Why is this less water going through, coming through? Okay, some other people, come on, not only Sean. But it's not really Jeffrey.
Because more water is stuck on the sides.
Okay, so there's more. What do you think I'm looking for? What's the word you think I'm looking for? Okay,
No clue.
Resistance.
Resistance. There's more resistance. The water has to rub against like more inner surface, so there's more resistance. Okay, I'll be back because my wife would be very, very, very unhappy if I told her here that I hung up on my sister-in-law. So hold on a second. Hold on a second.
Hey,
Hey, Max.
yo, Jason.
What are we talking?
Talking. Yes, you're talking. All right, good. So there's more resistance. So the more resistance there is, the more for the same power, the same voltage, actually, you have like less current going through. Okay. All right. Now, once again, here, if I have this here, if I pinch one, nothing will go through. If I pinch the other one, nothing, I won't be able to draw any water. Well, that's the same for a series circuits. I'm not just doing review of what you should have learned in grade 9. All right, so that's the characteristic of a series circuit. All right, so let me see here. All right, so series circuit, there we go. So a series circuit here, if this one burns out, well, the other one is not gonna work, right? It's like opening a circuit. So that's a characteristic here of a series circuit. Okay, the other one here is this. So I asked the student with one straw to do the same thing, to draw water for 2 seconds. Make sure that there's water in the straw first, and then drawing the water for 2 seconds. Take note of how much water in his mouth, and then to swallow it. And then instead of putting like one right after the other, I put them side by side. And I asked like the student to draw with the same power as before for 2 seconds. Make sure there's both draws have water in it. Take note of how much water he has drawn, his mouth, swallow it. Okay, so very easy here. So how much will there be like more water being drawn by the student, less water, or the same amount of water as for one straw? Okay, quick. There's a no-brainer here. Will there be? No? You don't know? Will there be more or the same? Yeah, Forrest.
There's gonna be more water.
Yeah, there'll be more. Why is there more?
Because you have less resistance. Because
Yeah, overall you have like there's another pathway, right? And there's less overall. There's less resistance. right? Okay, so that brings us to, of course, parallel circuit. Oh, just before I do this, now, hold on a second. Before I do this, now notice here that if I draw water here, if I pinch one, if I pinch one, there'll be water going through the other one. And there'll be as much water going through this other one as there was when there was only one. If I pinch the other one and then leave the other one unpinched, the same thing happens, right? So that's a characteristic of a parallel circuit. So what I've shown you here is an analogy for a parallel circuit. Okay, so parallel circuit. So let me see here. All right, it's a parallel circuit. Where's that parallel circuit? There we go. So is a parallel circuit. So this is the same circuit as before. It draws 1 amps. Now what happens here is I'm putting two loads, the same loads, in parallel. So notice here that I'm able to draw twice as much current from the source in such a way that you have 1 amp going through each source. If I put 3 loads in parallel, I'm drawing 3 times as much current from the source for the same voltage. In the same way as when I put like those, if I keep on putting like more and more of those straws in parallel, I'll be able to draw even more water, all right? Notice here that if one fails to function, right, the other one will just work just the same. And of course, it'll be, if one fails to function, now it'll go back to this diagram here. So it'll be able to draw only 1 amp now, right? And so on and so on. It looks like 11, but so only 1 amp, right? So this is a parallel circuit property of parallel circuits. Good. So, and the key point here to understand here is that when you put loads in parallel, you decrease the resistance of the circuit, allowing more current being drawn by the source. Yes, Madame.
So how come you could just like increase the current to like infinitely large by just adding a lot of loads?
That's exactly, well, I mean, it's, well, I'm not going to get into this. This electrical field, I mean, if you put 1 million of them, like, yeah, the electrical field, yeah, I have to think a little bit about this, but in practical terms, you're not going to put like millions of those in parallel, right? At your home, like all your outlets are, of course, placed in parallel. So that's why you're able to draw like as much that you draw, like, so if you put like, if you turn more and more devices at home on, you're drawing like more and more current into your house. And those outlets are placed in parallel because if you turn one off, you want the other devices to work as well. All right. Okay. Yeah, it's not a very good answer for this, but anyway, we'll leave it
question.
Yeah.
So does the resistance, like when you have 3 of the bulbs, does it not equal 27 ohms?
No, not in parallel. Okay, just wait. Okay. All right. So now this is the time for you like to take notes. Okay. This is my grade 9. Well, you don't see it because it's not going fast. Sorry, today it's a little bit long. Actually, I'm not going to share it now. Stop sharing. Okay. So remember this. Now, can I replace this? Can I replace this with a single straw whose length is the same as one of them, right? Can I replace this with a single straw whose length is the same as this? And I will have the same effect as these two straws next to each other in series? And if so, how would this single straw look like? So once again, so can I replace these two straw with one straw that would have the same length as this, and that would have the same effect as to the overall current going through it, or the overall? And if so, how would it look? Always the same people. Okay, raise, let me see here. Day. No, sorry. Yeah, day.
Would it have to be? It would have to be thinner.
Yeah, that's correct. So you would need like the radius a little bit thinner, right? Very good. Now, can I replace the effect of these two in parallel with one, same length, that would have the same effect as this? And if so, how would it look like? That's it, yeah?
It would just have to be like wider.
That's correct. Okay. So no matter how complex the number of loads you have, okay, you can always replace this with one big resistor that will do the same effect, okay? So this is called the equivalent resistance. So once again, like my grade 9 should have learned this. The other one, I don't know. I don't know if you were taught like equivalent resistance. I'm not so sure. Okay, so equivalent resistance. So time for you to take notes here. All right, so total equivalent resistance, also called like RT or REQE for equivalent. I prefer total. It's one symbol. So here, whenever you have two resistors in series, this is equivalent. You can replace this with one resistor, and this is very easy. The overall resistance will be the addition of the resistance of each of these, right? So the overall resistance here is equal to R1 plus R2. If there's more loads in series, then plus R2, R3, R4, and so on, okay? So you can always replace the effect of these two with one, where that one will have a resistance equal to the addition of the two. That's pretty easy, right? Now, when you put things in parallel, you remember the overall resistance goes down. The overall resistance of the whole circuit goes down. Now, you can replace these two resistors in parallel with one that will do the same job as far as resistance is concerned, overall resistance. And instead of adding, of course, the R1 and R2, what you add is you add the reciprocal. So 1 over the equivalent resistance, total resistance, will be 1 over R1 plus 1 over R2 plus blah, 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 blah. Okay, so if you have two, right. Besides those students I had in grade 9, have you guys, so give me a hands up here. Have some of you like learned this in grade 9? No? Max, you learned? Yeah. Okay, that's good.
Wait, like these equations and stuff? Yeah. Because isn't it in the textbook anyway?
By which textbook? In grade 9?
Yeah.
Really?
Wait,
no,
like,
I don't think it is. Another analogy
like
for Ohm's law? Okay, I don't remember. Jason, no, that's okay. That's a little bit far away. Okay, good. So this is just an example here. Okay, I would prefer, guys, that you do things in fractions. Don't do it in decimals as much as you can. So this is a little example here. Find the equivalent resistance for following circuit. So you have a 3 ohm in parallel with 5 ohm. So the equation is just this. You do this. Find the common factor. Not necessarily the lowest, but in this case, these are primes, so the lowest is 15, 3 times 5. You do this, and 1 over RT becomes 8 over 15 ohm. But don't forget, you have to flip it, right? So if you flip it, it becomes RT over 1. And so RT over 1 gives you RT, and this will be like 15/8. Right? Okay, so what's that? The chat here. Wait, but didn't we all do circuits in grade 9, Max? Yeah, but it depends on your teacher. Some teacher might not have taught this. Who was your teacher, Max? No, of course you were not in my class in grade 9. Oh yes, yeah, that makes sense, Ms. Chibano. Yeah, if you did it, then I did it. Don't understand, Forrest. You did what? I was in Max. Oh, you were in Max class, so with Miss Chibano. Yeah, that's good. Yeah, very good. Okay. Okay, so these series circuit and parallel circuit, they're the base. But there are some circuits here that are neither pure series or pure parallel. It's a combination, it's neither, right? So the next one here will be this here. So here, come on, going up. So the equivalent resistance for this one is 15/8. Okay, let me go a little bit up here. Okay, so this is a circuit here. All the loads here are neither in series or parallel. Remember, in parallel, the current must go through each device without going through any other device. So R2 is not in parallel with R4 because the current goes through R3 too, right? So yeah, so it's a circuit here that is neither parallel nor series. It's kind of a combination. And your goal is to find the equivalent resistance. So to replace all those 4 resistors with one big resistor that will sort of do the same job, that will draw the same amount of current as in this case here. Okay, so for those who had, Jason, you learned this in grade 9. What do we do? Having a bit of water. You remember?
Yeah, we group them first.
Yeah, so what we do here is you spot what is in pure parallel and pure series, and what you say, we collapse them, we replace this. That's correct. So here in this circuit, R2 and R3 are in pure series, right? The current that goes through R2 is the same as the one that goes through R3. So what you can do is, again, replace these two with one resistor that will do the same job as these two. So this is what comes next. Okay, so yeah, so A was find the total resistance of the circuit. All right, so what we do here is that we replace these two with one. And in order to keep track of which one we have collapsed, so it's 2 and 3, so we put like 2, 3. So R2 and R3 in series, so you get like R2 3 is equal to R2 plus R3, 2 ohm plus 6 ohm, and it gives you 8 ohm, right? Now, since I've already done this with my grade 9, I'm giving away like the next step, and then you repeat. So you ask yourself, is there anything that is in pure parallel or pure series? And then you collapse this. Yes, there is. R4 and R2, 3 are in parallel. Why? Because the current will split, go through each of these without going through any other load, and then rejoin right after. So R2, 3 and R4 are in parallel. Therefore, we can replace all this with one big resistor. Max, did you learn this also with Ms. Gibano?
I'm pretty sure we did, yeah.
Yeah, okay, good. All right. So you use the formula. So what's the formula here? Well, the formula is, whoops, let me just put this a little bit. All right, so the formula is to add the reciprocal, so 1 over R23 plus 1 over R4, so it's 1 over 8. R4 is 5 ohm. Then you find the common denominator, which is 40. Is it lowest? 5 times 2 to the 3. Yeah, it's lowest because it's all, yeah. Then you do your math. All right, so it gives you like 13 over 40. And that gives you like 40 over 13. So you replace these two with 1. And then you keep on going until you have 1 resistor. So is there anything in pure parallel and pure series? Yes, absolutely. R1 is in series with R2, 3, 4. So you know how to collapse this. So you just add them up. That's exactly what we're going to do here. All right, so this whole circuit here is being reduced to one big resistance here, called the equivalent resistance or the total resistance. Now, when you're left with your very last resistor, you don't have to put like 1, 2, 3, 4, and whatever. You just put T, right? So it's R1. So this is in series here. R1 plus this. Once again, I encourage you to use only fractions. So common denominator is 13, and here, voila. So this is the total resistance of the circuit. You could replace all these resistors by one big resistance, one big resistor of this value that will sort of do the same job as far as drawing the current is concerned. Okay, so we're almost there. Okay, B is find the total current. So IT, drawn by the source. Notice how I call this. I say drawn by the source. Okay, how much is being drawn by the source? Well, what you do here, well, you just use Ohm's law. So Ohm's law relates the voltage across. The voltage across this resistor is 15 volts. This is the total voltage. The voltage of the source here, VT, is the total voltage. And you just use Ohm's law here. So you have the total voltage, you have the total resistance, you're looking for the total current, then you just use Ohm's law. And then you isolate for this, and you keep, and if you can reduce, but I don't think you can reduce this, 79 is I think it's a prime number, probably, I don't know, 6, yeah, probably a prime number. Okay, are you good for that? Okay, questions? No questions? Okay, the last one here, I'll take like just a few minutes here, is the resistance in a wire. So wires do offer resistance, but there's very little. So I'll do this like very quick. It's pretty easy here. All right. So if you have a certain wire of length L, if you investigate like how much resistance there is across a wire as you change the length, you're going to find that the resistance is proportional to the length. So the longer the wire is, the more resistance there is. So if you have speakers at home, you want to minimize like the amount of wire that runs from the amplifiers to your speakers, because if you make it like too long, you're losing all this power from the amplifier. Some of it will be dissipated as thermal energy. So, and you want to supply your speaker with as much electrical energy as possible. The other one is the cross section. So it happens that the resistance is inversely proportional to the area. So the thicker the wire is, the less resistance there is. And so once again, you can sort of put those two relationships together. I think it's rho. I hope it's rho. Yeah, I think so. All right, so this is a formula here where rho is called the resistivity. Resistivity. So resistivity is the inherent resistance of a metal, okay? So because if you have like a copper wire, if you have a short and a long, they don't have the same resistance. But due to the copper alone, it's given by the resistivity. Okay? And then you can figure out like what the unit are. So units are, of course, so you want ohm here, you want to get rid of this, so it's going to be ohm, right? So this is meter divided by meter. This is meter divided by meter square, so you're going to have meter on the bottom. You want to have ohm here, so it's going to be like ohm times meter. Okay. Resistivity is a physical property of a material. Okay, so each material has like different resistivity, and the one with the lowest resistivity, I believe it's the copper. I believe. I'm not so sure if it's silver or copper, but I think it's copper. I might be wrong.
Wait, is it gold?
No, it's not gold. I think it's copper, but you can check this out and let me know tomorrow. I think it's copper. It's either copper or silver, one of those two. But I think it's copper. Okay, guys? Yes, okay, someone. Is it forest? Because forest, always like, it's silver. You see, I knew it was forest. So you sure it's silver? Forest? Yeah, okay. Mostly sure. Eric? Oh, no. Okay, so find forest. Find the resistivity of silver and copper. All right, and show this to me tomorrow. Okay, guys. What's that?
Silver is lower, I think.
It's lower?
Yeah.
Okay. All right, guys. So that's it. So you have like problems to do. They're not like terribly like difficult here. You might come across like one problem that you may not be able to do. So you may want to skip this and wait for tomorrow. But otherwise, you should sort of be able to do them all. Okay. If I can give this to grade 9s, you can do that. Okay. So questions? All right. So I'll see you tomorrow. And so I'll stay here like for 5 minutes. If some people may not have copied everything, I'll let them copy. Okay. All right. So take care, guys. God bless, and I'll see you tomorrow. Bye.
Sir.
Bye.
Yes, sir.
Mhm.